P-H-Y, papa, P-H-Y, P-H-Y, papa, P-H-Y. Physics. Welcome!
Welcome to another Honors Physics Camp lecture. Today we're going to be reviewing one-dimensional motion, specifically vertical motion, since we've already discussed horizontal in previous lectures. Yes, Alex, vertical motion is referring to objects in upward or downward motion, which is exactly what we're going to be discussing about today. So make sure that you take good notes and let's begin. Alex, what are you doing outside? Let's get back to our physics lecture. A well? What do you want a well for? A wish? What kind of wish? Come on, Alex, I think you should be focusing more of your time on studying rather than searching for a well to make a wish that you're going to get an A in physics. Now you're talking, Alex. We could determine what is the velocity of the penny when it hits the water or the depth of the well by simply knowing the amount of time that the penny was falling and its acceleration due to gravity. That's right, Alex. An object in free fall, such as a penny, will experience acceleration due to gravity. Okay, Alex, in order to figure out this physics problem, we need to draw out the scenario to better understand the object's motion. Notice how the penny will be dropped from the top of the well, in which it's going to fall towards the water at the bottom of the well. Thus, what do we know about the penny's motion based on this setup? Yes, Alex, you're right. The initial velocity is 0 meters per second, since it was at rest when it was dropped. And then as the penny moves downward towards the water, the velocity becomes negative to illustrate the direction of the object's motion being downward. What else do we know about a falling object? That's right, Alex. A free-falling object such as this penny will change its velocity every second at a rate of 10 meters per second squared. That's if we round that value of acceleration due to gravity. Okay, next we're given the time that it takes for the penny to hit the water, which is 6 seconds, indicating that this penny's velocity changed for a total of 6 seconds. Finally, we want to determine what is the penny's velocity when it hits the water and how much the penny traveled, in other words, the depth of the well. That's right, Alex. We could use a kinematic equation in this scenario because our acceleration due to gravity is constant. However, before we dive into using our kinematic equations, it's important for you to understand how much drawing out a physics problem can help you understand the object's motion. For instance, we know that the penny started at 0 meters per second at the top of the well, which is 0 seconds. Then, after 1 second, because of its constant acceleration experienced due to gravity, the penny's velocity changed to negative 10 meters per second. Then at 2 seconds, it was now negative 20 meters per second. At 3 seconds, it was negative 30 meters per second. At 4 seconds, it was negative 40 meters per second. 5 seconds, it was negative 50 meters per second. And finally, at 6 seconds, when it hit the water, it was negative 60 meters per second, which is actually one of the variables that we're looking for. But keep in mind that we could solve the same variable using our kinematic equations rather than having to go second by second. So now that we have covered the first step, which is to list out our variables, our next step is to find the right equation. Remember from our previous lecture that we saw 3 kinematic equations that could be very useful in constant acceleration scenarios such as this one. But there are 2 other equations that can also be used, giving us a total of 5 kinematic equations that can be used based on the variables given and which one we're looking for. Yes, that's right, Alex. It is important to remember that delta x is the same as saying final position minus initial position. So based on the variables given, you could rewrite any of these equations to consist of final position minus initial position rather than change in position. Okay, in our case, we want to know the depth of the well, in other words, the total displacement of the penny. Thus, we will be using change in position in these equations. Well, first we must color code our known and unknown variables and then determine which equation is appropriate for solving for the missing variable. Now remember, in order for the equation to be considered appropriate, it must only have one missing variable and the others should be known. Okay, so let's first try to verify the final velocity that we came up with from our drawing with one of these kinematic equations. Which one should we use? Good choice, Alex. We could use equation number 1 to solve for final velocity since we know the initial velocity was 0 meters per second, the acceleration can be rounded to negative 10 meters per second squared, and the time is 6 seconds, which means that we multiply negative 10 times 6 and then add to 0, and it results into negative 60 meters per second as the final velocity of the penny, which is exactly what we came up with from our drawing. Okay, next let's find out the depth of the well, which is basically searching for the displacement of the penny. And this is represented by delta x. Which equation would you want to use here, Alex? Great choice, Alex. Equation number 3 would be a great choice for our scenario because this equation consists of variables that we are given and only one that we do not know. Well, you're technically correct, Alex. Since we did solve for final velocity, we could technically use equations 2, 4, and 5 to solve for the missing displacement. However, just to be on the safe side, we could use equation number 3 since it has variables that we were given. Now, once I find the displacement, I could use equations 2, 4, and 5 to check if both of the variables that I solved for are valid. Okay, but first, let's start by solving for displacement using equation number 2, in which we know that the initial velocity is 0 meters per second, time is 6 seconds, and acceleration is negative 10 meters per second squared, which means that 0 times 6 results into 0, leaving us with only negative 10 times 6 squared divided by 2, resulting in negative 180 meters as the penny's displacement as it falls down the well, which means that the well's depth is 180 meters. Now to check our answers, we can select an equation that has both solved variables, then plug in those values and see if the equation is true. Which one do you want to use, Alex? Okay, so let's plug in our variables into equation number 4, in which displacement was negative 180 meters, and the final velocity was negative 60 meters per second, time was 6 seconds, and acceleration was negative 10 meters per second squared. That's right, Alex. After we simplify both sides, we end up with negative 180 meters equals negative 180 meters, meaning that both of our variables are valid for this scenario. Great job, Alex, in figuring out all of the penny's missing kinematic variables when dropped into a well. Good idea, Alex. What if instead of dropping the penny, you decided to toss it in the air with a velocity of 30 meters per second so that it could get a lucky penny toss? What air time would you expect before going into the well? That's right, Alex. The penny would take a total of 3 seconds to reach its highest point, in which the velocity would be 0 meters per second. Then it will travel back down for another 3 seconds, totaling to 6 seconds in the air before going into the well. So how would you figure out how much time the penny would take to hit the water and at what velocity? That's right, Alex. We could use the kinematic equation for this scenario, in which we know that the depth of the well from our previous scenario was negative 180 meters, and we know the initial velocity at the entrance of the well from our motion diagram was negative 30 meters per second. We also know the acceleration due to gravity. So which equation should we use to solve for the final velocity? That's right, Alex. We could use equation number 2 to solve for final velocity since we don't know the time and this equation doesn't require that variable. Okay, so what's next? Right again, Alex, we must plug in our values and solve for final velocity, which means that we must get rid of the squared by square rooting everything, resulting in a velocity of 67.08 meters per second. That means that that's going to be the penny's velocity when it hits the water. But what about the time? Which equation could we use to determine the time that it takes the penny to hit the water from the top of the well? Yes, Alex, equation number 1 would be a good choice. Like we mentioned before, we can technically use the variable that we just solved for, which was final velocity, to solve for our missing variable of time, unless we find another equation that doesn't require it and it has only one missing variable. And in this case, equation number 1 would be our best choice. So let's try it out, in which we will solve for time by rearranging our equation to final velocity minus initial velocity divided by acceleration, which will equal to time. Great job, Alex. Once we plug in our values, we will find the time was 3.7 seconds. So here's my question for you. How much time would it take for the penny to hit the water from the moment that you toss the penny in the air with a velocity of 30 meters per second? That's right, Alex. It would take a total of 9.7 seconds for the penny to hit the water at the bottom of the well, since we determined that it would take 3 seconds for the penny to go up in the air, achieving the highest point possible, in which its velocity was 0 meters per second. Then it began its descent back towards the well, taking another 3 seconds, and then we calculated that the total time from the top of the well to the bottom would be 3.7 seconds, resulting in a total of 9.7 seconds that the penny was in the air. This concludes our video lecture. Make sure that you took good notes, and that's it. Have a great one.